Hello everyone, I'm Zachary Steinberg and I'm a graduate student in the University of Maryland's Embedded Systems Masters of Engineering program, and this is my ENPM701 final project video. I took autonomous robotics in the spring 2026 semester, and I spent the past 16 weeks building an autonomous robot to compete in the class's grand challenge. In this video, I'm going to try and cover all of my work from the semester, including the robot's hardware components, its program functionality, and their software implementation. Now, I hope you sit back and enjoy the show. Introducing RB, the Autonomous Robot Bale or Block Extractor. The theme for the course this semester was agriculture tech. We can imagine that RB operates out in a field collecting agricultural bales and transports them to a drop-off zone on a farm. In the class's Grand Challenge, RB needed to collect 9 blocks from the Grand Challenge arena. The arena was a 10-foot by 10-foot square. RB started in the 2-foot by 2-foot landing zone and had to collect colored blocks from the cluttered environment area. After RB collected a block, it had to bring it to the 4-foot by 4-foot construction zone. RB will continue collecting blocks until all 9 blocks have been delivered to the construction zone. Now let's build RB. RB is built from the DF Robot Baron 4-wheel drive mobile platform kit. The kit comes with 4 motors, 4 wheels that are each mounted onto a motor, and 2 optical encoders that keep track of wheel rotation. One encoder is attached to the front left wheel, and the other is attached to the back right wheel. The kit also comes with a battery pack that powers RB's motors through a transistor H-bridge. Both the battery pack and the H-bridge are connected to a physical switch on the robot. When the switch is closed, power flows from the battery pack through the H-bridge to RB's motors. When the switch is open, no power is able to flow through the H-bridge. When the Baron kit is fully assembled, this is what it looks like. To interact with the world, RB has a number of sensors and a gripper actuator. RB uses a Pi Camera 2 module to capture video input, an ultrasonic distance sensor to avoid collisions with walls, an IMU sensor that's connected to an Arduino Nano to help localize and orient itself, and the previously mentioned optical encoders to keep track of the distance RB is driven. RB also has a gripper actuator connected to a servo motor that's used to grab our target blocks. To process all of the sensor input, control the motors and actuator, and orchestrate all of RB's functionality for the Grand Challenge is the Raspberry Pi 4 Model B. Here's a pinout diagram that represents the RB system. Please note that the Arduino Nano is connected to the Raspberry Pi via USB. Before programming RB to tackle the Grand Challenge, I had to build out core functionality for RB that could be used as a foundation for my Grand Challenge implementation. At a high level, the features implemented were perception, locomotion, and localization. For RB's core perception functionality, I used OpenCV to process video from the Pi Camera 2 module and applied HSV masks to isolate, detect, and track different objects based on color. In this video here, I'm tracking the green light from the stoplight image I'm holding. Additionally, I implemented the ultrasonic distance sensor, and it's able to provide its measured distance in centimeters. For RB's core locomotion and localization functionality, I implemented motor control using IMU and encoder data and RB's servo gripper. In the video here, RB is programmed to drive forward 50 centimeters. The motors are controlled by a pulse width modulator. To drive the correct distance, I calculate the number of encoder ticks needed to drive the 50 centimeters by using the circumference of RB's wheels and the number of ticks that are measured per wheel revolution. When RB has counted the target number of encoder ticks, it has reached the correct distance and will stop. In this video, RB is programmed to pivot 180 degrees. When pivoting, RB uses the IMU to keep track of its orientation. RB keeps track of how far it's pivoted, and once its pivoted angle equals its target angle, it will stop. Here, the gripper is opening and closing. The gripper's servo motor is controlled using pulse width modulation signals and has duty cycle values for the gripper's open and closed positions. The gripper's open duty cycle value is 7%, and the gripper's closed duty cycle value is 2.5%. Now that we've built core RB functionality, it's time to get started with the Grand Challenge. As a reminder, during the Grand Challenge, RB needs to retrieve blocks from a collection zone and then transport them to the designated drop-off zone. RB must collect a red block, a green block, and then a blue block in that order. In total, RB must collect 9 blocks and transport them to the drop-off zone. For the Grand Challenge, I implemented a Python class called Robot. What you're looking at here is the robot class diagram with its parameters, functions, and subclasses. Some of the robot class parameters include an internal position, a drop-off zone position, a task list, and PWM objects for its left motors, right motors, and gripper servo. Robot also has functions to move forward and backward, pivot left and right, search for blocks, grab blocks, and drop off blocks. The robot class has an IMU reader object that starts the IMU and gets data directly from the Arduino Nano. The robot class also uses the PyCamera 2 Python module, the PWM object from the Raspberry Pi GPIO library, and uses an enum called color to keep track of which color block it's supposed to grab. Before implementing any Grand Challenge code, I designed a finite state machine for RB to follow. For each task, RB will have to search for a block. After validating that the block is there, RB will need to track the block and align itself with the block. Once RB is aligned, RB will open its gripper and approach the block. If RB loses alignment during the approach, RB will re-enter the tracking state and align itself again. Once RB is close enough to its target block, it will grab the block by closing its gripper. Next, RB will navigate to the drop-off location, release the block, and begin again to search for its next block. The first task RB needs to do in the Grand Challenge arena is search for a block. Here, RB is searching for a red block. The search function will pivot RB 140 degrees. If a block has not been detected, RB will pivot back 140 degrees, drive forward 20 centimeters, and then search again. In the video, RB pivots until it finds the red block. After finding the block, it stops. We can see this from RB's perspective too. As soon as the red block enters the frame, RB stops because it has identified the block. Once RB has identified a block, it needs to track that block. RB uses OpenCV for image processing and applies HSV masks to its video input. The HSV masks are used to identify contours in each video frame. From these contours, we can apply bounding boxes over the detected blocks in the video frame. If the bounding box is not aligned to the center of the frame, RB will pivot until the block is centered on its screen. Here, we can see the video captured from RB's camera and how RB pivots to keep itself aligned with the block. If the block's bounding box is left of center, RB pivots to the left. If the bounding box is right of center, RB pivots to the right. The next key step in our finite state machine is grabbing a block. Once RB has successfully searched and tracked a block, it needs to approach and grab the block. During the approach stage, RB checks to make sure the block's bounding box is still centered in the middle of its frames. If not, RB enters the tracking state again until the block is centered. Once it is close enough to the block, RB will then close its gripper and secure the block. In the videos you see here, RB is able to successfully align itself with the block, approach the block, and grab the block with its gripper. To navigate to the drop-off zone, RB compares its current position with the drop-off zone's position. Each time RB is in the drop-off zone, it updates the drop-off zone position in the robot class. First, RB calculates its distance from its current location to the drop-off zone using the distance formula. Then, it calculates the target heading it needs to face using the ATAN2 function. Using the target heading, RB finds the shortest angle to turn. RB will then pivot towards the drop-off zone and drive forward the calculated distance. Unfortunately, during the Grand Challenge, I was not able to successfully bring any blocks into the drop-off area. During this run, we can see that RB is able to drive forward to the drop-off location and orient itself towards the collection zone. It's able to successfully track and grab a red block, but when it's tasked with bringing the block back to the drop-off zone, it over-pivots and starts driving towards the incorrect location. I suspect that this is caused by an IMU data buffering issue. When pivoting, I relied solely on the IMU data. From time to time, the IMU data streamed from the Arduino gets delayed. When this happens, the robot is not able to properly calculate the distance it has pivoted, resulting in overpivoting. I suspect this happens due to a GIL bottleneck. Python doesn't support standard threading the same way that C++ does. So if a computationally heavy task takes too long, the thread will get delayed and the Pi doesn't have the latest, which then results in overpivoting. Here's a video of a test run from Arby's perspective. It's able to successfully grab a red block and drop it off in the drop-off zone. When it tries to drop off the next block to the drop-off zone, it overpivots again and misses the drop-off area. Overall, my implementation wasn't robust enough to repeatedly and reliably return blocks to the drop-off area. So what's next for this project? First, I want to fix and improve my approach to the Grand Challenge. My implementation flat out didn't work the way it was supposed to. Next, I want to run the code on a microcontroller. Most likely, it will be on an ESP32. Then, I want to convert the working Grand Challenge code to C++ and implement the core functionality as tasks to run concurrently. And finally, I want to implement the code with a real-time operating system like FreeRTOS. Overall, I had an awesome experience in ENPM701 and would highly encourage anyone to take this course if they are studying engineering at University of Maryland and enjoy building cool things. I want to thank Professor Mitchell for all of his help throughout the semester and being a great resource of information. I want to say thanks for watching, and I'll see you in the next one.